So the third category of the reactions in that question is substitution. Substitution reaction. Substitution reactions. Actually, alkanes are less reactive and chemically inert, but in the presence of sunlight H mu, photochemical reaction. Photochemical reaction occurs, and photochemical reaction occurs. The alkanes react in the presence of sunlight, though they are chemically inert and less reactive in the presence of sunlight acting as a catalyst. Chlorine reacts with the alkanes. So suppose if I am taking, that is ethane, CH3 single bond CH3 gas plus chlorine gas in the presence of sunlight, H mu acting as catalyst, acting as a catalyst, you get here CH3 single bond CH2Cl plus HCl. This is called ethyl chloride. It is called ethyl chloride. It is called ethyl chloride. So this is one of the important reaction which you have to understand in the case of substitution reactions of, that is, alkanes. So here, if you go for the next part of the question, ethine or acetylene when treated with the O2, product obtained is why air is not treated. Why air is not treated with the ethine? Because the answer is, for this question, the answer is air is a mixture. It contains oxygen, it contains nitrogen, it contains carbon dioxide, it contains carbon monoxide, inert gases, and even that is carbon monoxide gas, mixture of carbon monoxide gas, nitrogen gas, oxygen gas, okay, and other hydrocarbons are present. So that means if air is mixed, suppose if you are treating with the, and here nitrogen is chemically inert, nitrogen because of its stable structure, nitrogen is not that easily, it is going to react in the chemical process. But if you go for oxygen, yes, it's highly reactive because it contains unpaired electrons in its structure, it is highly reactive. So for example, in the mixture of ethine is also called acetylene. Ethine is also called acetylene. So I am taking acetylene here, that is acetylene, CH triple bond CH plus half mole of O2 gas, oxoacetylene flame. You can write here CH double bond CH with one oxygen. We can call this as oxoacetylene flame. It has a temperature of not less than 1800 degrees centigrade and it is used for welding purposes. This oxoacetylene flame is used for welding. Oxoacetylene flame is used for welding purposes. Similarly, the next part of the question is conversion of, next question, conversion of ethyl alcohol, conversion of ethyl alcohol to ethanoic acid, conversion of ethyl alcohol to ethanoic acid, ethyl alcohol to ethanoic acid is an oxidation process. Why? Is an oxidation process. Why? The reason is because when you go for ethyl alcohol, here the answer is, if you go for ethyl alcohol, the formula is C2H5OH is ethyl alcohol. Then you can go for ethanoic acid. Ethanoic acid, it is CH3 double bond, carbon double bond oxygen, single bond oxygen, ethanoic acid. Ethanoic acid is also called acetic acid. Acetic acid is also called vinegar. Vinegar, this vinegar 5 to 8% of acetic acid in water, it cools to give glacial acetic acid. Call this as glacial acetic acid. So I repeat here, the ethyl alcohol, so a conversion of, so conversion of C2H5OH to acetic acid is an oxidation process. Why it is an oxidation process? Because ethyl alcohol when it is added with the nascent oxygen with the oxidizing agent with an oxidizing agent, that is KMnO4, in the presence of base, this KMnO4 in the presence of base, potassium permanganate in the presence of base, it is called Bayer's reagent. It is acting as an oxidizing agent. So it supplies the nascent oxygen, and this nascent oxygen will convert the alcohol to that is CH3 carbon double bond oxygen to carboxylic acid. This is carboxylic acid. So we are converting an alcohol to carboxylic acid with same number of carbon atoms. Here we have 2 carbons. In ethyl alcohol we have 2 carbons, so N is equal to 2. N represents the number of carbons. In ethanoic acid or acetic acid also we have number of carbons too. So therefore the number of carbons are remaining same, and the conversion of ethyl alcohol to ethanoic acid is oxidation, because this reaction requires an oxidizing agent. The oxidizing agent is Bayer's reagent. Bayer's reagent is called alkaline potassium permanganate. Alkaline means base, potassium permanganate, alkaline potassium permanganate, we call it as base reagent. This base reagent supplies the nascent oxygen to the ethyl alcohol. This ethyl alcohol contains an alcoholic group that is called primary alcohol or simply alcoholic group. In the ethyl alcohol, the primary alcoholic group is getting converted to the carboxylic group. Once the carboxylic group is formed, we are successfully converting the ethyl alcohol to the ethanoic acid or the ethanol to ethanoic acid, and overall the process is called oxidation process because the nascent oxygen is involved by the oxidizing agent. So the next part of the discussion is general properties of ethanol. If you go for the general properties of ethanol, that is general properties of ethanol. This ethanol, it is colorless, soluble, liquid, colorless soluble liquid. It is used for it is medicinally it is used in tonics, syrups, and syrups. Then consumption of alcohol consumptions leads to health problems like drowsiness, stupor, damage of liver, the other case of damage of the metabolic activities. And this alcohol, to make this alcohol, it's a good solvent actually. This ethyl alcohol is also good organic solvent. It's a good organic solvent to impart color, mixed with the dyes. It is mixed with dyes, and sometimes to make it unfit for drinking purpose. Making it unfit for drinking purpose. Unfit for drinking purpose. Drinking or consuming purpose. The ethyl alcohol is mixed with the methanol. This is methanol. This mixture we call it as methylated spirit. So the next part of the discussion is the chemical properties of ethyl alcohol. So in this chemical properties of ethyl alcohol, chemical properties of ethyl alcohol. If you take ethyl alcohol, in this that is number one, action of metals. Example, sodium, potassium. So C2H5OH aqueous plus sodium solid gives rise to C2H5ONA plus half mole of H2 gas. This is aqueous. So this is ethyl alcohol, and this is sodium methoxide, and this is half mole of hydrogen gas. This is half mole of hydrogen gas. So that means whenever a metal, this is a metal, sodium metal, when it is acting on the ethyl alcohol, this hydrogen is called as acidic hydrogen. Actually, this hydrogen which you are able to see in ethyl alcohol, this is acidic hydrogen. We call this as acidic hydrogen, and we got sodium methoxide, evolution of hydrogen gas. And similarly here, if you go for this ethyl alcohol, if you take, that is, it can react completely with the base, action of directly bases. Example, you can take NaOH, sodium hydroxide. So C2H5OH of aqueous plus NaOH of aqueous gives rise to, that is, C2H5ONA plus H2O. This is nothing but alcohol is a weak acid. It is a weak acid reacting with strong base to form salt and water. That's why this reaction, you can call it as neutralization reaction. We can call this as neutralization reaction. So here, ethyl alcohol is a weak acid, sodium hydroxide is a strong base, and when a weak acid is reacting with a strong base, it is able to give sodium methoxide, that is salt, along with the formation of water. This is aqueous. Here the aqueous, what do you mean by AQ? AQ means it is water as solvent. Because ethyl alcohol can ionize in the presence of base only if you are taking water as a solvent. That's why we mentioned the ethyl alcohol as alcohol aqueous, we mentioned the base as base aqueous, and we mentioned the salt as aqueous, and water is of course liquid. So this is a kind of neutralization reaction. So the next part of the discussion is alcohol as a fuel. Next topic, alcohol as a fuel. If you take alcohol as a fuel, ethyl alcohol, actually this when you say alcohol is nothing but ethyl alcohol, which is C2H5OH, which is also called ethanol. Manufacture of ethanol or ethyl alcohol can be done through, that is, molasses. Actually, you take cane sugar. This cane sugar is nothing but C12H22O11. It's a carbohydrate. It's a disaccharide. So take this C12H22O11, you dilute it with water. This is solid, this water is liquid. Dilute it, excess, you get C6H12O6, 2 molecules. This is glucose. Glucose, when it is subjected to fermentation, fermentation, you get ethyl alcohol plus carbon dioxide. So this ethyl alcohol, this is nothing but this alcohol which is obtained is called absolute alcohol. Now finally what is happening here is this ethyl alcohol, if it is used as a fuel, this ethyl alcohol can be used as a biofuel, because ethyl alcohol, when it is subjected to combustion, gas subjected to combustion, it is giving carbon dioxide gas plus water liquid plus large amount of energy. So this principle, this is the combustion principle. That means heating the ethyl alcohol in the presence of oxygen, it is giving carbon dioxide gas, and it gives water as liquid. This water which is obtained as a liquid is called water vapor, which can be used for drinking purpose, and it's a carbon dioxide emits less smoke. So therefore we can use ethyl alcohol as a fuel or simply biofuel, and it's a common principle. It is used for the generation of energy, and combustion of ethyl alcohol is, therefore it can be an exothermic reaction. It's an exothermic reaction. It is an exothermic reaction. So the next part of the discussion is properties of acetic acid. Properties of acetic acid. So if you take acetic acid is also called ethanoic acid, which is the IUPAC name. Structure, if you take molecular formula, C2H4O2 is the molecular formula. O2 is the molecular formula. Take this C2H4O2, the structure is CH3 single bond carbon double bond single bond oxygen. So what you are noticing here is this acetic acid, because it contains one carboxylic group. This is the carboxylic group. And we have number of carbons too. So therefore we can write this as, root word is ethanoic acid, because CH3 COOH contains COOH group, it is a carboxylic acid. We take this carboxylic acid. This carboxylic acid, if you dissolve in water, CH3COOH in the presence of water, when it is subjected to cooling, it gives CH3COOH aqueous. CH3COOH aqueous, this results in the formation of glacial acetic acid. It results in the formation of glacial acetic acid. So all these are the general properties. It has acetic acid has low melting point, which is equal to 290 Kelvin. So cooling is rapid. is rapid. So if that is the case, these are all some of the important general formulas of the acetic acid or ethanoic acid, and the structure is, this is the structure of the ethanoic acid, CH3COOH, wherein which it contains one carbon double bond oxygen and one single bond OH. So the next part of the discussion is, let us study some important properties of acetic acid. This acetic acid, that is chemical properties, chemical properties in this. A, esterification. What do you mean by esterification? Esterification is nothing but, that is carboxylic acid plus alcohol in the presence of small amount of acid acting as catalyst, it forms ester plus water. This ester which is formed gives a fruity smell. So this is somewhat like a test. So this is a test for detection of carboxylic group. So what is the kind of reaction which is possible? So if you go for the reaction, in the case of esterification, if you go for the reaction, you can take the reaction like this, that is CH3 single bond carbon double bond oxygen OH, this is aqueous, plus ethyl alcohol OH of C2H5OH of aqueous, reversible reaction, add small amount of H plus ion, this is acid, catalyst, acid catalyst. So the product obtained is, here you can see one molecule of H2O is removed out, and you are going to get CH3 single bond carbon double bond single bond oxygen C2H5OH. This is called ethyl acetate, which we call it as ester, and this is the ester group. This is the ester group. So this is nothing but esterification. So this is a test for the esterification of carboxylic acids along with alcohol. When alcohol is added to the carboxylic acid in the presence of small amount of acid, mineral acid, that is add 2 or 3 drops of HCl to the acetic acid and ethyl alcohol, and you just shake it for a few seconds, and then you take it to the Bunsen burner, and in the presence of Bunsen burner, if you heat for 2 or 3 minutes, the hot vapors, sweet smelling vapors are obtained. The sweet smelling, that is fruity smell, it gives the fruity smell, it gives the smell of a fruity smell. That fruity smell compound is nothing but ester. Here the ester is, that is ethyl acetate. The formula of ethyl acetate is CH3 single bond carbon double bond oxygen single bond OC2H5 is ester. So once the ester is formed, that fruity smell is confirmed. Once the fruity smell is confirmed, that means we have detected the carboxylic group. We have detected the carboxylic group in the carboxylic acids. So this is the test for carboxylic acid in the form of esterification. Next, second one is go for saponification. Of soap. Saponification of soap. So we got an ester. Ester, when treated with base, we get ester when treated with base, we get salt, fatty acid, fatty acid we are going to get. So let us see what is that we are going to get. So take one example. Now take this ester, that is CH3COO, CH3 COO of O, C2H5 of O, C2H5. You add it with the base. Ester is treated with base. This base, it is irreversible reaction. So you find that you get CH3 CONA, CH3 single bond carbon double bond O, Na plus C2H5 OH. So you got salt plus alcohol, salt plus alcohol plus alcohol, but here alcohol is a weak acid. So this principle involved is nothing but the principle involved in this reaction, conversion of ester to the salt, conversion of the ester to the salt is nothing but that is saponification of soap. So this soap is used in that is removal of dirt from the surface of the cloth, and here we can understand because we are speaking something about the soap, I would like to also explain the next part of the discussion, that is I'll continue the discussion. The next part of the discussion is cleansing action of soap. In the language of chemistry, what do you mean by soap actually? In the language of chemistry, when you speak about soap is nothing but, when you take soap is nothing but salt of higher fatty acid. Salt of higher fatty acid is nothing but soap. Chemically, when you define soap or when you understand soap in the language of chemistry, what is soap means, simply you have to say salt of higher fatty acid. So what are the salts of higher fatty acids? Example, you can take sodium stearate, molecular formula C17H35 COO of Na is sodium stearate. So let's continue the topic, that is cleansing action of soap. In this cleansing action of soap, as already I told you, this for soap, if you take the example soap, example sodium stearate, if you take molecular formula C17H35 COO of Na. So this C17H35 COO of Na is a solid. You are dissolving it in water, that is liquid, and you are going to get C17H35 COO of Na aqueous. So I can take one negative charge and one positive charge. So what is happening here is, if you break the bond, this is where the bond is broken. This is stearate ion, and this stearate ion is having two ends. Take this stearate ion, 17 carbons are there. So C17H35 COO minus can be taken as, we can conclude this as it contains two ends. It has two ends. One is hydrophobic end, another one is hydrophilic end. So hydrophobic end is solvent heta, and hydrophilic end is solvent lava. Hydrophobic is also called lyophobic, and hydrophilic is also called lyophilic end. So whatever, if you take the stereoion, so take the stereoion, that is CH3, CH2, CH2, CH2 and so on. CH2, COO of O minus. So this is, you can see that this is the polar head, hydrophilic, and this is this chain which you are able to see, this chain which you are able to see is hydrophobic. So what is happening is, if you take a soap solution, that means it contains the hydrophobic end, which is called tail. Hydrophobic end, this is the tail region, this is tail end, this we call it as tail end, and this is head end, this is the head end. So what is happening is, like soap solution acquiring minimum concentration in the form of CMC, critical micelle concentration. What is CMC? CMC is critical micelle concentration, or critical micelle concentration. Suppose CMC I am expanding. What is CMC? This CMC is called critical micelle concentration. This critical micelle concentration, it forms an envelope around the dirt molecules. So when you go for dirt is nothing but here, when you go for dirt is nothing but oily substance insoluble in water. So if you think that this is the dirt, and you're finding that all the micelles can form an envelope like this. This is the dirt and it forms an envelope. You can see the free Na plus ions. Na plus ions are freely moving in the solvent. So this is the dirt molecule. These are dirt molecules, and these are the micelles. And you find that dirt plus micelle involves in emulsification. Dirt molecules, when they comes in contact with the micelle is a part of soap solution which contains both the ends, that is the hydrophobic ends and the hydrophilic ends. Hydrophilic ends, they are insoluble in water, so they penetrate into the dirt molecules and they reach the exterior of the surface of the soap solution, and the friction is being created between the dirt molecules. Between the dirt molecules and the micelle, there is a kind of mechanical friction taking place. Because of the mechanical friction, a process involves between the dirt and micelle is emulsification. Emulsification is nothing but breaking of dirt molecules. breaking of dirt molecules into individual particles. So through this mechanism we can say that the dirt molecules are going to be removed from the surface of the cloth, and the cloth is free from all the dirt layer present over it, and soap plays a very important role in removal of the dirt. That's nothing but cleansing action of soap, and this is the concept of soap. So the next part of the discussion is, that is, let us have some exercise. First question, number of covalent bonds involved in C2H6. So here the answer for this is C2H6 is molecular formula of C2H6 compound is, name of the compound is ethane. So because it is ethane, we can show the structural formula. We can take it in the form of, that is CH3 single bond CH3. This is the condensed structure, expanded structure, CH3 single bond CH3. We can write it in the form of carbon single bond hydrogen, carbon single bond hydrogen, 3 single bonds of hydrogen. So you can count the number of sigma bonds, sigma, 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 sigma and sigma. So in total you have 7 sigma bonds, also 7 covalent bonds. Because of equal sharing of electrons, a sigma bond is formed. A sigma bond is nothing but a covalent bond. Because we got 7 sigma bonds, we can go for 7 covalent bonds. So that is the first question. So go for the second question. Draw the Lewis electron dot structure of ethanoic acid. Ethanoic acid A, B propanol, C fluorine molecule, D that is butanone. So if you go for ethanoic acid, first one ethanoic acid, underline eth, underline oic. So it means root word, oic means carboxylic acid. So root word, because it means root word means number of carbon. There are 2 carbons. You can take 2 carbons here. So one is 1 and the one is 2. Because it is carboxylic acid, chain terminating. So what I am doing here, take double bond oxygen, single bond OH, then satisfy the tetravalencies. Now go for the Lewis electron dot structure. We can take carbon is tetravalent, hydrogen is monovalent, carbon contains 4 valence electrons, carbon has element, I'll take it like this, element, valence electrons. If I take element and valence electrons, if I take hydrogen, number of valence electrons are 4. If I take carbon, hydrogen number of valence electrons 1, carbon number of valence electrons 4, oxygen number of valence electrons 6. So here you can take, there are 1, 2, 3, 4 hydrogens are there. So 4 into hydrogen is equal to 4 into number of valence electrons 1, which is equal to 0, 4. Carbon, there are 4 carbons, 4 into carbon, each carbon number of valence electrons 4, so 4 into 4, that is 16 valence electrons. there are 6 oxygens, so 6 into oxygen, which is equal to 6 into 6, 36. So this is total, this is 12, 12 plus 4, 16, 16, 4, 5, 56. So 12 plus 4, 16, 4, 5, 56 electrons are there. 56 electrons are there in ethanoic acid. 56 electrons are there. So here take the carbon. Carbon we have 4 valence electrons. So if we take this particular carbon, 1, 2, 3, and this is 4. We have each hydrogen 1, 2, and 3 hydrogens. So use a cross. Here also you try to use a cross. Then we have another carbon. So again 1, 2, 3. Now 1, 2. You can take it like this. 1, 2, 3, and we can take 4. And rather you can use oxygen here. Oxygen if we take 1, 2, 3, 4, 5, and 6. You go for one more oxygen and one more hydrogen. So 1, 2, 3, 4, 5, and 6, and one valence electron of hydrogen. So here we can create one bond here. Here one bond is formed, here one bond is formed, here one bond is formed, and here one bond is formed. Here one bond, here one bond, and here one bond is formed, and here one bond is formed. So this is the Lewis electron dot structure. You can see one bond formation here. Here you can see one bond formation. Here you can see one bond formation. Here you can see one bond formation. Here you can see two bond formations, and here you can see one bond formation, and here you can see one bond formation. So therefore you can take here carbon single bond hydrogen, single bond hydrogen, single bond hydrogen, hydrogen, then here single bond carbon double bond oxygen, 1, 2, 3, 4, 2 lone pairs, 2 lone pairs, again single bond oxygen, 2 lone pairs, single bond hydrogen. This is the Lewis electron dot structure of acetic acid. So this you condense it again. See H3 single bond carbon double bond oxygen, double bond oxygen, double bond oxygen, again single bond oxygen. So this is acetic acid. Similarly, if you go for the second one, that is propanol. If you go for propanol, likewise propanol, Lewis electron dot structure prop known. So there should be 3 carbons, 1, 2, 3, double bond, and you have 2 single bonds. Take hydrogen, hydrogen, and hydrogen, single bond hydrogen, again single bond hydrogen. So what you are noticing here is 2 lone pairs of oxygen. So bring this again, take it here. So here you can take 1, 2, 3, 4, again you come over here, 1, 2, 3, take the oxygen. So here 1, 2, 3, 4, 5, and 6. So here again you take another carbon, 1, 2, 3, and 4. So here you mark one hydrogen, here you mark one hydrogen, here you mark one hydrogen, here you take one cross. Okay, so here yeah, this is one hydrogen, this is one hydrogen, this is one hydrogen. This is one hydrogen. So a bond is formed here. Here one bond is formed. 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 Here one bond, two bonds here. So this is one covalent bond, covalent bond, covalent bond, covalent bond, covalent bond, and this is covalent bond, and this is also covalent bond, and this is also covalent bond. So therefore finally we can just take the same structure, that is C, single bond hydrogen, single bond hydrogen, carbon double bond oxygen with two lone pairs. Again, that is same product we are getting here, same product. Rather what I am going to do is I am going to just show it like this, because already I have expanded the first structure, so I can show it like this: CH3, again CH3. So this is the final product. This is going to be the final product, Lewis electron dot structure product. So like this you can draw Lewis electron dot structures for the given compounds.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.